Hello, we're back with another matrices video, and depending on the order in which you've been learning matrices content, it's possible by now that you know how to add them, you know how to subtract them, you know how to multiply them, you know how to find determinants and maybe even inverse matrices. But after doing all that, you're still not actually sure, why do we even care about matrices? Why are they useful? Well, one of their uses is in the use of transformations, and therefore that's what we're looking at today, how to do matrix transformations in 2 dimensions. But before we fully get into things, we need to know how to apply them, and also it's probably worth mentioning you've come across transformations as an idea in general, maybe on more than one occasion by now, depending on what you've learnt so far. You might have come across them at a very early stage by looking at them from a visual standpoint, looking at rotations, reflections, enlargements, and translations, and seeing how if you apply them to a shape on a graph, how that shape will visually change based on the transformation you applied. It's also possible, depending on how much of the A-level content you've studied, that you've come across transformations again when we came across graph transformations. And that was focused more on how transformations affect the algebra of equations of graphs. Now, when we're looking at matrix transformations, this does have more of a link to the much earlier transformation stuff I mentioned, but instead of just looking at stuff purely from a visual point of view, we're now trying to apply a more rigorous mathematical, numerical application to that stuff and trying to be able to specifically calculate, okay, if we have this point, where is that point going to move to based on whatever transformation it is we are applying to that point. The way matrix transformations are applied is we start off with a 2 by 2 matrix, which represents the transformation you're trying to apply. If you're doing matrix algebra, you could label that whatever you like. I'm going to label it in this case M, but it depends on what you've called your transformation, what letter you might use to represent it. But of course, a 2 by 2 matrix is one with 2 rows and 2 columns, and whatever numbers inside are whatever numbers are necessary to carry out whatever matrix transformation it is you're trying to apply. That matrix is then going to be multiplied by the position vector of the point that you're trying to transform. If you don't know what that term position vector means, it basically means converting coordinates to a column vector. It's the same numbers as coordinates, just therefore written in a different way. So the structure would be x, y, and if we're writing it in matrix algebra, sometimes we just use the letter x to represent a coordinates sort of matrix, if you will. And when you multiply these two matrices together, that is what will result in your transformed point, the position vector of that point after it's been affected by that transformation. And therefore, if we're doing matrix algebra, we often represent that by writing the x again to point out we're still talking about a point, but then put an apostrophe next to it to make it clear it's the transformed version of that point we'd seen before. And therefore, similarly, if we're looking at it in terms of the actual matrix itself, 2 by 1 matrix with the transformed x coordinate and the transformed y coordinate in it. Nice! So that's how you apply a matrix transformation, but let's actually start looking at the specific transformations themselves. What transformations do we need to know how to deal with? Well, the first ones you need to know about are stretches and enlargements, and that's good because they're quite simple ones. Basically, they're strongly related to the identity matrix. First of all, looking at a stretch scale factor A parallel to the x-axis. It's ultimately just going to be the identity matrix, but instead of the ones, one of the ones is going to be replaced with your scale factor. If it's a stretch parallel to the x-axis, it's the first of the ones that gets replaced with your scale factor. All the other elements of the matrix are the same as what they would normally be for a 2 by 2 identity matrix. So there you go, that's a stretch scale factor A parallel to the x-axis. If you're doing a stretch scale factor B parallel to the y-axis, it's the same idea. Again, rough structure of an identity matrix, but this time the scale factor is replacing the other one of the ones that normally appears in the identity matrix. So now the 1 will be up there, 0's in the other diagonal, and then the B will be down here. Nice. And then lastly, hopefully you remember from before that an enlargement is just a stretch That's happening in both the x direction and the y direction at the same time, both with the same scale factor. So therefore, enlargement scale factor k with a center at 0, 0, because a reminder, enlargement needs a center of enlargement as a reference point. Therefore, the matrix for that would be k, 0, 0, k. Basically, either view it as a combination of the matrices above, but with the same scale factor for both of them, or view it as just the identity matrix with both of the ones replaced with the scale factor. It's worth mentioning that technically the a, the b, and the k should be positive numbers, because if they are negative numbers, that's actually implying that more than one transformation's happened. You've had both a stretch or enlargement and a reflection, because although mathematically, numerically, it's the same as a stretch scale factor minus 1, we in reality call a stretch scale factor minus 1 a reflection. So it's better if you do separately list it and word it as a reflection if you see a negative scale factor, but I just thought I'd make you aware of that. It's also worth pointing out some examples aren't so fussy about that and accept you describing it as a stretch with a negative scale factor, but I personally don't like that, so I've avoided describing these transformations in that way. It's worth mentioning that all the transformations currently on the screen right now are all ones that are not in the formula booklet, and therefore you need to remember them off by heart. Good news is though, they're all fairly logical, and because of their strong relationship to the identity matrix, they're all fairly easy to remember off by heart. Okay, the other transformations you need to know are rotations and reflections. So if we want to do a rotation of an angle of theta degrees anti-clockwise about 0, 0, several different aspects of that. It's important we're mentioning it's a rotation. It's important we're mentioning how much a rotation it is, which is decided, of course, by the angle. It's important mentioning the direction, because anti-clockwise versus clockwise would end up with a different position for the thing we're rotating. And also, the center of rotation is quite important as well, because just like enlargements, you need a reference point so you know how the object is rotating. Worth mentioning, I've said that the angle is in degrees. There's no mathematical reason why you can't write it in terms of radians, if you know what those are yet. And in fact, the mark schemes will generally at first write the degrees answer as the first written answer, but they will have somewhere in the notes the equal answer in terms of radians, because there's no mathematical reason why you can't write them in radians. Okay, and the matrix for this particular transformation, this rotation, looks like this. So once you've decided what your theta value is, you then plug it into all the trig functions, and whatever numbers those come out, well, that's the 2 by 2 matrix you need to multiply to do the rotation transformation. You also need to know how to do reflections, and a reflection in the line y equals tan theta, lots of x, that is a tan theta in brackets before it's being multiplied by the x, will be represented by this matrix. You'll notice it looks awfully similar to the rotation matrix, just with thetas replaced with 2 thetas, and the minus sign in a suspiciously different place. But worth pointing out that when we're saying y equals tan theta lots of x, that's because the tan theta is representing the gradient of the line you're doing the reflection in. Worth mentioning when I'm talking about that angle theta, it's talking about the angle between your line of reflection and the positive x-axis. So for instance, if you want to reflect in the line y equals x, a line with a gradient of 1, that's talking about theta being 45 degrees, because that's the angle it makes with the positive x-axis. And in fact, funny enough, if you look at tan of 45 degrees, it is equal to 1, so it does tally up there. Cool. Things to be aware of though this time are that the transformations that are on the screen right now are luckily ones that are in the formula booklet. Hooray! That means you don't need to remember these ones off by heart. You just need to be aware to look for them in the formula booklet. It's also worth pointing out that therefore when you're describing them, the key things with these ones are about deciding what theta is, and then also making sure you're using the correct terminology to describe them, making sure you're not missing out any of the criteria we discussed for both of these transformations that I've also written on the screen right now. Cool, no worries. But the problem is, how are you going to know out of these two transformations which is happening? These are a bit more difficult just by instantly glancing at them to know which of the two transformations is happening in a particular scenario. The key thing you're going to be wanting to look out for is the position of the minus signs, because that changes depending on which of the two matrices you're looking at. And what you're looking for is actually more specifically a change of sign. If your matrix is a reflection matrix, then the change of sign is in this diagonal here, the main diagonal. I've described that diagonal as before in some of the other videos. So if you're looking for one of your numbers to be positive while the other's negative in this main diagonal, you instantly know some sort of reflection has probably happened. Whereas if there's been a change in sign in the other diagonal, then going from bottom left to top right, then the change of sign is like that for a rotation. So just looking for where the change of sign is occurring in your particular matrix is enough to let you know whether it's a rotation that's happened or whether it's a reflection that's happened. Controversially, there is arguably a sixth transformation that some students need to know for some A levels called a shear. But note I'm being very careful there to say the word some, and that's because there are some A level exams where you don't need to know what a shear is. And in fact, for the exam board I teach, you don't need to know what the shear transformation is. So therefore, I'm not going to cover the shear transformation in this video. I might make an extra video on it at some point. So just be aware of the fact that you might see some online resources and other places that describe it, and therefore not to worry. Depending on what exam board you're doing, I will probably write a note in the descriptions of this video making it clear which exam boards you do or don't need to care about the shear for. And so that means we're ready to start doing some examples. So this first example is concerned with applying transformations to the point with coordinates 5, 6. Of course, as we said earlier, in order to be able to apply transformations to a point, you need to rewrite the point as, well, earlier I called it a position vector, but in reality I guess I should have called it a 2x1 matrix. Basically just the same numbers you see in the coordinates, just written as a column vector sort of format. Part A, enlargement scale factor 2, center 0, 0. We only deal with enlargements with a center 0, 0 for A level, so therefore that's not going to really affect the question much, but the scale factor will, because it means it's basically going to be an identity matrix with the 1s being replaced with 2s and the 0s in their normal place. We then multiply that by 5, 6, because that's how we apply matrix transformations. I'm not sure I made that clear enough earlier. If we're ever doing any linear transformations, it's always this format. The matrix transformation written first, then multiplied always afterwards by the 2x1 matrix representing the coordinates. Okay, and then therefore multiplying that out, that'll be the first row of the transformation times by 5, 6, which is 10. The second row times by 5, 6, which will get us 12. And therefore we're done. And that answer does completely make sense if you think about it. Of course, enlargement scale factor 2 with the center 0, 0 is just going to double both the x and the y coordinates. Then on to part B, we're doing reflection of the line y equals root 3x. That square root sign, of course, is only above the 3, not above the x, and therefore we can simply identify that the gradient of our line of reflection is root 3, which is important because that can now help us identify what the theta is in the formula, because tan theta, we said before, was equal to the gradient. So therefore tan theta is equal to root 3, and that's an equation we now need to solve to find theta. Now there are multiple solutions to that equation, but we're only interested in the first one we come across, which can be found using arctan. So arctan of the square root of 3 is 60 degrees. Good stuff. Okay then. So worth pointing out, the reason we don't care about in the others is because they're all going to be separated by 180 degrees, and if you're on a straight line and you rotate it another 180 degrees, you still have the same straight line. Okay, so now we've got our value of theta, we can now plug it into the structure provided by the reflection matrix, which is cos of 2 theta, so that would be 2 times 60, which is 120. Sine of 2 theta, so sine of 120, sine of 120 degrees, and then lastly minus cos of 120 degrees. That will again just be multiplied by 5, 6, And admittedly then you can start to do some simplification. Of course, cos of 120 and sine of 120 are numbers that can be found. Cos of 120 is just going to be minus a half. Sine of 120 is just going to be root 3 over 2. So therefore this is the matrix we're applying it to. Minus half would be positive half in that bottom right hand corner. And although I admit it's not going to be particularly nice numbers, when you multiply these two matrices together, you will get minus 5 over 2 plus 3 root 3 as the x-coordinate of the transformed point. And then also doing the same thing with the other, we'll get 5 root 3 over 2 plus 3. And there we go. Not very nice, but those are the transformed points. Something worth pointing out for exam technique, my question was quite open-ended. It did just say transform the point, didn't ask what format it wanted the final answer in, but sometimes they will be more specific and ask for what's the coordinates the point will be after it's been transformed. And if they ask for coordinates, of course be aware that what I've written here and what I've written here is not coordinates. Those are 2x1 matrices, so you would need to rewrite your answer in the format of coordinates, even though it's the same numbers still. But if they ask for it in a particular format, you must give it in the format they ask or risk losing at least 1 mark. On to a second example, and this time instead of applying a transformation, we're having to identify what a transformation is based on the matrix that's representing that transformation. Worth pointing out that if you're being asked to do this, it's kind of got to be one of the sort of transformations we've already looked at before, one of the ones you're meant to have pre-existing knowledge on. So that helps narrow it down straight away, particularly as then there's almost a sort of checklist of things you can check for to know which of those transformations it's then going to be. The first thing I check for is how similar is the matrix we're trying to identify. How similar is it to the identity matrix? Because if it's very similar to the identity matrix, instantly know it's going to be a stretch or an enlargement. So if we look at this matrix, we instantly look at it and go, wait a minute, that looks very similar to the identity matrix. The only thing that's changed is the bottom right hand corner 1 has been replaced with a 5. So therefore instantly I know, if you think back to the stretches and enlargement sort of formats of matrices we had earlier, this must be a stretch because only one of the ones has been replaced with a different number. It must be a stretch parallel to the y-axis because it's the bottom right hand corner one that's been replaced. And lastly, it's important to point out that that number then decides the scale factor, so therefore it's a scale factor of 5. Cool, so therefore we've done with that one already. On to example 3, where again we need to identify the transformation represented by the matrix. First of all, like before, you compare the matrix to the identity matrix. How similar compared to the identity matrix is it? If it is similar, then you instantly know it's enlargements or stretches. But if it's not, like this matrix is, probably going to be a rotation or reflection. So then, how do you know which one it is? Well, I already told you earlier, the difference between them is about looking for where the change of sign happens. For this one, the change of sign is happening on this diagonal, which is not the main diagonal, and therefore, because it's happening in this diagonal, therefore I know that it must be a rotation matrix. So, we know it's rotation, but we've got to decide the angle in order to be able to fully describe this transformation. So to do that, you need to set up some equations. To do that, you compare the rotation matrix in the form booklet to the matrix you've been given. So this is the generic matrix for a rotation according to the form booklet. And from that, you can set up some mini simultaneous equations. From this, you realize that cos theta must equal minus root 2 over 2. And also we realize that sine theta must equal positive root 2 over 2. You've got to solve both these equations to find out what value of theta works in both of them. Common mistake students sometimes make is they'll just solve one of the equations, they'll get the first answer they get from it, and they'll just accept that as the final answer. So for instance, we could solve sine theta equals root 2 over 2 by doing arc sine of root 2 over 2, which is 45 degrees. And some students will make the mistake of going, oh, the answer is therefore 45 degrees. But you don't know that yet. You've got to find a second solution between 0 and 360 degrees. A way of doing that, of course, would be to do for, as its sine, 180 minus the other angle. So our two potential values of theta are 45 degrees or 180 minus 45 degrees, which is 135 degrees. Therefore, we don't know currently which of those two it's going to be, so that's why we also need to solve this second equation and see what value of theta works in both. So therefore, start by doing arc cos of minus root 2 over 2, and that will get you 135 degrees. Now, admittedly, we can already see, therefore, which the final answer is going to be, because we've got one that matches, but just a reminder, if you're solving an equation for cos, you get a second solution by doing 360 degrees minus. So therefore, you do 360 degrees minus 135, which would be 225 degrees. Cool. So therefore, what is the angle that works? Well, the only value of theta that works in both equations is 135 degrees. So that's the value of theta for our rotation. So the final answer is it's going to be a rotation. So you've got to mention that. You've got to mention the direction the rotation's in. If you're using the form booklet, it's always automatically assumed to be an anti-clockwise rotation. The angle, which is the value of theta we decided already, so 135 degrees. And then also, as the form booklet mentions, the fact that it's about the origin. So you can either write about 0, 0. Also, sometimes they accept about O, capital O, which is meant to be the letter representing the label for the origin. There you go. So make sure you do mention all those parts if you want to get the marks on this question. If you miss out any of those bits of information, they can dock you marks if you haven't fully described a transformation. Also worth pointing out for identifying rotations and reflections, as I said, it's the change of sign on depending on which diagonal it's on. That decides whether it's specifically the rotation or specifically the reflection. And then to find the value of theta, if it's a rotation or a reflection, it's about setting up these equations involving sine and cos, solving them both, and find the value of theta that works for both equations, crucially. Okay, hopefully you found this video useful. I'll see you in a future video where we'll be looking at how do you identify what's going on if more than one transformation has occurred, as well as some other things. Goodbye.